I will be starting in-person classes here in Asheville, North Carolina soon. If you would like to join and attend an in-person class here in Asheville, North Carolina, please click on the Silicon Dojo meetup link down below. Welcome back. As you know, I am Eli, the computer guy, and in today's class, we're going to go over TCP/IP version 4 subnet masking. Now, before you try to run away in horror, or you try to crack a beer to drown the misery your brain is about to go through, one of the things I want to explain to you is that subnet masking is not actually very difficult. Subnet masking is actually pretty simple, and frankly, in the modern world where you have things like cheat sheets, it's something relatively easy to implement and to deal with, but it's one of those things that the human brain just has difficulty dealing with. Subnet masking is the perfect example of why technology professionals get paid a lot of money to do simply what seems to be simple tasks. When you look at subnet masking, it seems to actually be a pretty simple task, but for some reason, when most people take a look at it, their brains melt. Their brains melt. So if you can understand subnet masking, then you can go out there and you can make money because you can do things that are actually pretty simple that make other people's brains melt, and so therefore they need your services. So today, again, we've talked in the past, we've talked about the Ethernet technology, we've talked about TCP/IP version 4 in general. So today what we're going to be talking is about subnet masking and why subnet masking is important. So the first thing that we have to keep in mind when we start talking about subnet masking is to think about what TCP/IP version 4, the problem that it's trying to solve. And the problem that TCP/IP version 4 is trying to solve is your ability to manually configure a network so that you can constrain what computers or devices or servers can talk to what other computers and devices and servers. Again, when we talk about layer 2 networking technology, again, we're talking about switches. Switches use MAC address, media access control addresses, to identify all of the computers that are connected to the switch. And in that world, again, more or less, those MAC addresses are hard-coded to the hardware. So you as an administrator, you as a network professional, really can't do a lot of manual administration. So what TCP/IP version 4 allows you to do is this allows you to manually configure networks to essentially say who should be talking to who else, who shouldn't be talking to who else, and the whole 9 yards, right? So that's an important thing just to keep in mind when we start talking about TCP/IP version 4. Now, when you see an address, so normally I'll talk about this like 192.168.1.10, right? This is the IP address. One of the important things to understand about an IP address is this is not simply the identifier for the computer or device on the network, again, the server, the computer, the print server, whatever else. This also has a network identifier in the IP address. So one portion is the network identifier, the other portion is the computer identifier. So essentially the first component is an identifier for the network, and the second component is the identifier for the computer itself. This is very important because remember, TCP/IP version 4 is a routable protocol. You are able to separate different networks using a router, and so that router sends communication between different networks, and so computers actually have to be on a different network for the routers to work, right? So if we have our switch here and we have all of these computers connected to the switch, and this is 192.168.1.x. I'll explain this later. And this, connects to a router, which then connects to another switch, right? If this network over here is 192.168.1.x, if these are the same networks, right? If you have manually configured this to be the same network, then basically this router is not going to function properly because you have the same network on either side. It will fail. So what you need to do is you have one network over here, that's 192.168.1.x, that gets connected to a router that then connects to another switch, and this could be 192.168.2.x, right? It is a different network. So when a computer on this network tries to communicate, can't find the computer it's looking for in this network, it will then go to the default gateway, which is essentially the router. The router will then route that traffic to the network that it's connected to, and it will be able to find the computer that it's looking for. So that's one of the important things to be thinking about when we're talking about these IP addresses, is that the network component is very important, especially when you're dealing with routers, because if you manually configure the router to essentially have the exact same network on either side of the router, you're going to run into problems. And where this can be a real issue, especially with new people, right, is you have your switch here, and on your switch you have DHCP, and you have DNS, and you have Active Directory, and you have all of your host computers, right? But that's 192.168.1.x. One of the issues is people just aren't thinking about it. And so they have, DNS on this side, they have DHCP on this side. And so DHCP will not go through the router. DHCP is Dynamic Host Configuration Protocol. This is what dynamically assigns IP addresses to the different computers on your network. So that won't get routed through the router. Basically, the router will be the wall for DHCP. And so you can run into a real issue where you have these two networks that somehow got manually configured to be the exact same TCP/IP network number, and then your router is going to fail because it's not able to route traffic. One of the other things to be thinking about, this is not prominent in the 2020s. But again, do remember when we're talking about Ethernet and we're talking about TCP/IP, one of the biggest problems here is we're dealing with 50-year-old technology. Remember, Xerox came out with Ethernet in 1973. Look at what the current date is and do some math and realize how long ago that was. So when Ethernet first came out, a lot of the tools and a lot of the ways that we architect the networks nowadays just simply didn't exist before. So one of the things that they wanted to do in the past, especially when they were dealing with hubs, remember hubs? All hubs are splitters, right? Basically, all your computers connect to a hub, and then when one computer wants to communicate with another computer, the traffic goes into the hub and out every single other port on that hub, and essentially it generally becomes a disaster because you get something called a broadcast storm, and it's very horrible. It was wonderful. I mean, in 1973, it was cutting-edge technology. Not so much anymore. But one of the things back then, when networking equipment was very expensive and the whole 9 yards, one of the things I thought is, hey, what if we want some computers that are connected to a hub to be able to communicate with each other, but we don't want those computers to be able to communicate with other computers that are connected to the hub. And so that's one of the things with that network identifier 192.168.1.x, right? Basically, you could create this network for these computers, and then you have 192.168.2.x. This would be the network for these computers over here. So although they are physically connected to the same, essentially a splitter, it was essentially a splitter at that time, they would not, with TCP/IP version 4, they would not be able to communicate with each other. We are logically splitting the network. You may have wanted this in the past for any number of reasons. Maybe these computers were for like the lab, so maybe you had a computer lab, and these computers were for the administrators. And they connected them all to the same switch. Yeah, not a smart idea in the modern world. But again, if you go back to 1973, that might have made half a bit of sense. And so basically, with the network identifier, you can tell computers essentially who they should or should not communicate with. In order to have 192.168.1.x be able to communicate with computers on 192.168.2.x, you actually then have to put a router in between, and essentially the router will route the traffic between the two networks. One of the important things to think about here, though, and this is where things get really kind of sort of stupidly complicated in the technology world, is if you have a hub. So if you have a hub, and this is a splitter, so when a computer on 192.168.1.x wants to communicate with another computer on 192.168.1.x, that communication will go in to the hub. So the hub is just a dumb splitter from 50 years ago. That would actually go out every single port on that hub. Only 192, the computer in the 192.168.1.x network will actually respond to the communication, but it is important to understand that all that traffic would be going out to every other port on that hub. And so that's where, if you had both of these subnets essentially on the same hub, you can run into communication problems. You're like, oh no, but this is one network and this is one network, so they won't screw with each other. And it's like, sort of. Sort of, you can run into problems. When I am talking about this, if you know a little bit about technology, it's important to understand I am not talking about VLANs. VLANs is where you can virtually divide your physical switch into different VLANs, so VLAN 1 and VLAN 2. This is not a VLAN type thing. This is not a Ethernet. This is not a data link layer, an OSI model layer 2 issue. This is all about doing the configuration up at that TCP/IP4 level. So basically, that's some of the things to be thinking about here. And so when we talk about the IP address and we talk about the network component and we talk about the computer identifier, it's important to understand that the network identifier says what network the computer is on that it's communicating with. For one network to communicate with another network, you need a router in the middle. If both networks on either side have the same identifier, it will fail. So basically, a router has to be used to communicate between two different networks. So this is 192.168.1.x, and this is 192.168.2.x. So those are two different networks. So routing can occur. And if you really want to create a disaster, using your switch, or hopefully you don't have a hub at this point, you can actually separate the communication of all of your computer devices connected to that hub or switch simply by putting them onto different subnets. So now the question is when you're looking at this IP address and it's 192.168.1.10, how do I know as a technology professional that the network identifier is 192.168.1.x, as we say, and the computer identifier is that 10? How do we figure that out? We understand that by using something called a subnet mask. So whenever you go into your computer settings and you pull up your IP configuration settings, you're going to see your IP address, and right under that you are going to see your subnet mask. So for 192.168.1 let's say 10, basically this is called a Class C subnet, and so the subnet mask would be 255.255.255.0. And so what this shows us, once we understand how the numbering scheme works, is essentially that 255.25.255, that shows me that 192.168.1, that is the network identifier, and then wherever the 0 is, that shows me that that's the computer identifier on the other side of that. And so basically, if you're looking at this from a real cursory example, let's say the 10.1 network, so 10.1.10.5, right? This is considered a Class A network. The subnet mask for Class A is 255.0.0.0. And so basically what I can do is I can take a look at this and go, okay, I see the 255 stops here. So everything that is above the 255, that is the network identifier. Everything that is 0.0.0, that is the computer identifier. And so very simply, what the subnet mask shows you is it literally shows you where the network identifier ends and where the computer identifier begins. So at this point, you're probably thinking, well, this is pretty simple. I don't understand why people's brains get melted, right? Okay, so there's this 255 thing. So basically, whenever I see the 255, that means what's above it for the IP address. That's the network identifier. And wherever I see the 0, that would be the computer identifier. So there's something called a Class C subnet, and there's something called a Class A subnet. But that all seems to make a lot of sense. Why would anybody's brain melt over something like this? But one of the things that's probably going through your head, what is this 255 thing? Like why 255? Not Why not 5,025? Why not 10? Where does this number come from? And that number comes from the place where that's going to melt your brain. So whenever we're taking a look at this, again, we'll see these numbers, right? 10.1.10.5, right? These numbers actually come from something called an octet. So you have 4 octets. What an octet is a string of bits. Bits are either 0 or 1. They're on and off. So when you look at 255.0.0.0 or 10.1.10.5, basically these are 4 octets. So octet is 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8. Right, so let's just imagine that's all actually all separated out. And so when you take a look at these numbers, like 255, so 255.0.0.0, what that is 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, and 0 all the way to the end, right? So that's actually how we get to the number of 255, is essentially by counting up these bits. But then you sit there, but I don't understand. So you have a bunch of ones, you have 8 ones. So that should be 8, right? Where'd you get 255 from? I don't understand. Okay, so now let's go and take a look at the actual octet itself. So we got 1, 2, 3, 4, 5, 6, 7, 8, right? So this is an octet. The octet, again, each one of these dashes essentially represents either a 0 or a 1. And then they have a number identifier. So on the right-hand side, how is that for you? Anyways, over here, I'll just put it this way. Over here, this starts with the identifier of 1. Then it goes to 2, then it goes to 4, then it goes to 8, then it goes to 16, then it goes to 32, then it goes to 64, and then it goes to 128, right? And so if we say .1, so when we say 192.168.1.1, right? If we're trying to see this in the bits of an octet, what that would be is this would be 1, and all the rest of these would be 0. So when you're going through and you're counting up the numbers, like not 128, not 164, not 32. Oh, okay, so 1. So okay, so that's how we represent this. When we talk about a subnet mask of subnet mask of 255. 255 is where these are all ones. And so you add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And then that is what gets us to the 255 there. And so this is how the octets work and when we're looking at this numbering system. So if you go here and let's say you're looking at 190, let's see, so 192.168. 1.25. So if we take a look at this at 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 4, 8, 16, 32, 64, 128, right? So we take a look at this. If we're trying to figure out the bit in the octet, how to represent 192, then it would be 1 for 128 and 1 for 64, and then 0 for everything else, and then that should get us to 192, right? If we go back and we look at 168, let's see if I can do my math properly. So let's see. So that would be 128 plus I'm horrible at math. 20, no, it's not 80, so it wouldn't be that. So that would be 0. 128 plus 32, so 128, so that would be 30, that would be 60. So that gets us to 160. Then this would be 0, then this would be 1, 0, 0, 0, right? So 128 plus 32 plus 8, I think gets us to 168. If that is wrong, it's not the technology, it's my really crappy math. right? And that's how we're able to identify this in bits. This will matter in a little bit when we go into subnet masking. Again, when we look at 1, so again, that would be 0 all the way across, just the identifier over here for 1. If we're looking at 25, right, so 25 would be 16 plus 8 would be 24. Again, plus 1 would be 25. So the identifier for 25 would be 0, 0, 0, 1, 1, 0, 0, 1. And that's how we use the octets to get to these different numbers. And so each one of these numbers here, so 192 is represented by an octet. 168 is represented by an octet. 1 is represented by an octet. 25 is represented by an octet. Same is true with the subnet masking. Again, we do 255.255.255.0 as a subnet mask. There's actually octets here. So 8, 8, 8, 8. Right? And so this is how we come up with the numbering scheme for these octets. And then once you understand that, we're going to go to how the actual subnet masks work, and hopefully this will make a lot more sense. So at this point, we understand an IP address contains both the network number and the computer number or the device identifier for the network. We also understand that the subnet mask is what tells us where does the network identifier end and the device identifier begin. And I just explained to you how the octet numbering system works. Now let's bring this all together so that you can see how the subnet mask actually works when you're looking at these octets, so that you can understand this, when you start dealing with TCP/IP networking in the future, right? So okay, let me do this. So we have 192.168.1.1. So this is the IP address, and then that has a subnet mask of 255.255.255.0. Right? And so we know, simply because I've told you, then that means that this 192.168.1 is the network identifier, and the 1 is the computer identifier. How this works out with the octets, right? So we have the IP address octet, so it's 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8. Let's just hope there's 8 in there. Anyways, now we have the subnet mask, right? So the subnet mask is underneath. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8. Let's say dot. 1, 2, 3, 4, 5, 6, 7, 8. So when you're looking at the subnet mask, essentially the network identifier ends where the ones end. So if we have what is called a Class A subnet mask, I'll talk about this in the future. Basically, for the subnet mask, you would have 1, 2, 3, 4, 5, 6, 7, 8, right? And then everything else would be 0. So if that's the case, we then know that this is the network identifier and this is the computer identifier. So there's a subnet mask scheme, 10.1.10.5, let's say. It has a subnet mask of 255.0.0.0, right? So if you put these together, 1 plus 2, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128, that will get you 255. And so then we know that in this, the network identifier is 10 because the subnet mask is only is 255. When we look at this, this up here is a Class C subnet, 255.255.255.0. So what that means is this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, oh, no, over there. And so basically, so this is, all filled up. So that's 255. This is all filled up. So that's 255. And this is all filled up. So that's 255. And so we can see here using these octets, this is the network identifier. And this is the computer identifier. And that's where these subnets come from. And so basically that's the thing, is when you're looking at the numbers, whether it's 192, whether it's 255, basically you're going through and you're just, you keep going until there's a break and how many in the ones, and that's when when the network identifier is one side and the computer identifier is on the other. So why this works out is because when you're sitting there and you're trying to figure out how to divide up your computers, there's a limited number of computer identifiers and there's a limited number of network identifiers, right? So basically when we're sitting here, and if we have a class C subnet, 255.255.255, we only have the final octet to be able to use to be able to get the IP address for computers in this particular network. And with that, you get a maximum of 254 different IP addresses that you can have on this particular network. As you're able to get more octets into the computer side, you're able to get more computers onto your network, but the number of networks goes down. So in a class C, right, a class C subnet, 255.255.255.0, this allows you to have 254 computer IP addresses and a metric crap ton of network addresses. Again, if you need to have a huge number of network addresses, this gives you that ability. A class A subnet, on the other hand, 255.0.0.0, this then gives you only 254 possibly network addresses. I think it's 254, something like that, 256 maybe. But then it gives you a metric crap ton of IP addresses that you can use on that particular network. So when you're designing your network, one of the questions is going to be is how many IP addresses do I want on my local area network? It's basically computers that'll all be able to communicate with each other, and how many different networks am I going to need to be able to break everything out? So when you're looking at this is all it is when we talk about the subnet masks. So now you're looking at those octet numbers and you're probably getting a little confused, right? Because when we have the octet, so 1, 2, 3, 4, 5, 6, 7, 8, right? And this is 1, 2, 4, 8, 16, 32, 64, 128. One of the things I just said in the previous section is that if you have a class C subnet, so 255.255.255.0, that in a class C subnet, you're only going to have 254 IP addresses that you can use for the devices on your network. Again, your servers, your print servers, whatever else. And you're probably sitting there and you're like, well, wait a minute, but if we add all of these together, we get 255. So why am I only able to get to 254? And the reason for that is the uppermost number and the lowermost number in an IP address range are actually used for specific things. So with the 254, to get to the 254 addresses here, the lowest number in that particular network would be 0. That is the network identifier. So when you go and I talk about the, so we say 255.255.255.0, 0 is actually the network identifier. So we cannot use that as an IP address number. If we add all of these up and we get to 255, we can't use 255 because 255 is the broadcast address. So if you have all of these computers that are connected to a switch and one computer needs to try to communicate with every other computer in the IP address range, it can use the uppermost number, that 255 address, to do a broadcast and actually broadcast out to all of the other computers within that subnet range to try to communicate with them for any particular purpose. So the lowest number is 0. That is the network identifier. And the highest number, 255, that is the broadcast address. So when you look at this, theoretically, you can have 256 addresses. One would be 0, one would be 255. So this is where they talk about 256 minus 2. Whenever you're trying to figure out how many usable IP addresses you have in a range, you count out up the numbers, then you do minus 2, because the lowest number is the network number, and the highest number is the broadcast address number. So now, as we've been talking about IP addresses and subnet masks, I've been talking about subnet classes. You will hear me talk about class A, class B, class C. There's also actually class D and class E, but we're generally not going to worry about these. This is not a CCNA class. You want to deal with class Ds and Es, go to your CCNA class. Essentially, when we talk about the class of IP address, this is just a simple way to explain more or less how many 255s we're dealing with, right? So when you have a class A subnet, basically that means it's 255.0.0.0. So if I say this is a 10.1.10.15 address on a class A subnet, I then know that 10 is the network identifier, and everything past that is going to be the computer identifier. We have class B subnet, that is 255.255.0.0. So the first 2 octets, those are used as the network identifier. The last 2 are used for the computer identifier. And the subnet mask you're generally going to be using a lot is class C, and that's 255.255.255.0. And basically for this, what this means is the first 3 octets are the network identifier, and the final octet is the computer identifier. That will give us up to 254 individual IP addresses for whatever network that we're dealing with. And so you're probably sitting here like, well, that's not too bad, right? This all seems pretty easy. But here's an interesting question, right? One of the important things to be thinking about as a technology professional is to remember you're going to be interacting with systems, you're going to be interacting with other administrators, and many times, essentially what other administrators are going to do is they're responsible for the whole network, and then they're going to give you like a little chunk of the network for you to play with, right? So let's say, you're working for a large enterprise type company, and the main network operations folks, they say, okay, we're going to give you an IP address block, and we're going to give you 192.168.1.x subnet, right? So that's a 255.255.255.0 subnet mask, and you can do with it as you will. So that gives us 254 potential IP addresses within that particular subnet block. And so you're given these IP addresses and the subnet mask to build out your infrastructure. But then you're sitting there and you're thinking about it. And you're like, well, let's see. I have this one LAN. So I have a LAN. And on this LAN, I have my Active Directory server, my DHCP server, and my users, right? That's the important thing. My users are on this one LAN, and let's say I've got 100 users, I don't know, plus 10 servers that are on this particular LAN. But we also have this database application thing, right? So we have a cluster of database servers, and we'll talk about clusters in a different class. But essentially, we have a cluster of database servers. And you know what I really want to do? I want to put them on their own individual LAN. And I don't want users to be able to willy-nilly be able to see the cluster. Right? When we take a look at things like ransomware attacks and other things, the reason things like ransomware attacks are able to occur is because users' computers are able to see things such as the database cluster. If a user's computer can see something, it can attack something, and then everything goes to hell. So, as a high-level administrator, one of the things that I want to think about is how to segregate my networks, how to separate my networks, so that different devices and computers can only talk to and can only communicate with the computers and devices that they should be communicating with. And this is where we use routers, and we use firewalls, and we use a whole bunch of stuff we're going to talk about in a different class. And so, what I think about here is like, if I could connect these two local area networks with a router, most likely also with a firewall there, and then only the appropriate traffic could go back and forth, that would be a wonderful thing. But what does a router do? What does a router require? A router requires two different networks. This has to be one network identifier, and this has to be a different network identifier. But at this point, I've only been given one network identifier. I have 192.168.1.x network. And so how am I going to make this work out? How you make this work out is by thinking about your subnet mask slightly differently, right? So we look at these octets. Oh, 1, 2, 3, 4, 5, 6, 7, 8, period. 1, 2, 3, 4, 5, 6, 7, 8, period. 1, 2, 3, 4, 5, 6, 7, 8, period. 1, 2, 3, 4, 5, 6, 7, 8, right? So these are the 4 octets that we're used to. 1, 2, 4, 8, 16, 32, 64, 128 is the scheme. So whenever you're dealing with Cisco equipment, whenever you're dealing with something that's very network heavy, one of the things that you'll see how they denote subnet masks, instead of saying class A, class B, class C, they'll do a slash. So they'll do 192.168.1.10 on a /24. And so what this means is we use the first 24 bits as the subnet mask, and then the final 8, that's what's actually used for the computer identifier, right? So currently we have 192.168.1.x, and we got /24, and so this is the network identifier, and this is the computer identifier. But I have been given this to play with as I want. So what I can do is I can additionally essentially add to the subnet mask to be able to divide my networks into 2 different networks. So I can add an additional network identifier. So since I've been given 24, what I can say is, what I want to do? I want to steal one. I want to steal 1 bit out of this class C subnet, and I want to use that as a network identifier so that I can create my 2 networks. And that way I have networks that the routers can deal with. And so what happens there is then you do 192.168.1, let's say 10 as the IP address, /25. And so when you say the /25, that means you're bringing in that additional bit. And so this will be part of the network identifier, and then the other part, that will be the computer identifier. When you do this, we then actually come up with 2 networks. So then we have a .0 network, and we have a .128 network. So with this, essentially you get an IP address range of .1 through .126 for the first network, and you get an IP address range of .129 through .254 for the second network. So the 1.126. So if I have an IP address of 192.168.1.5/25, then this can see 192.168.1.25/25. It can see 126/25. So all of these would be in the same subnet. 192.168.1.200/25 would be in a different subnet, and that is where you would need the routers to be communicating between the 2. And so that's how you can be given a subnet range for yourself at an institution, and then essentially basically grab the additional octet bits here to decide how many networks that you need. Do you need 2 networks? So a /25 will give you 2 additional networks. A /26 will give you 4 additional networks. A /27 will give you 8 additional networks, and go from there. Now, when you're doing this, you can go through and you can figure out all the numbering. You can figure out all the numbering, you can figure out all the networks. Or And I'm going to tell you this. I want to tell you this because I remember when I was in your shoes, you can also use a cheat sheet. You can also use a cheat sheet. When I'm looking off to the side, I'm actually using a cheat sheet here. So this is just a little subnet mask cheat sheet that I found, and this kind of shows you the different things that you can be thinking about when you're doing the subnet masking, right? So basically, this shows us here on a /30. This is only going to give us 4 addresses for 2 hosts, because remember, the lowest address is used for the network number. The highest address is used for the broadcast number. So since you get 4 addresses, you can actually only use 2 hosts. This gives you the net mask here, and it goes through. If you go down here, we can see the different things. So if it's /25, it gives you the network numbers that you can use. It gives you the IP address ranges that you can use, and it gives you the broadcast address. A /26, it tells you, it'll give you 4 additional subnets, .0, .64, .128, .192. This will give you the IP address ranges that are useful there, and so on and so forth. But this is basically the basics of how the subnet mask system works. Essentially, think of it as where the ones end, 1111111, where that ends, that is where the subnet mask ends. That is the identifier for the network. Everything past that is the computer identifier that you're going to be dealing with. So now that one of the questions that's probably coming up in your mind is, you keep hearing me talk about like 192.168.1.x or 10, .x.x.x. And one of the questions is where am I getting these IP address ranges from? So when you go to create an IP address range within your network, where do these numbers come from? Am I just kind of pulling them out of my butt? And the reality is no, I'm being told what these numbers are. I'm being told what these numbers are, right? So if you're out and you're on the full-fledged internet, right? You have a data center that is connected directly to the internet. Somebody there is going to be telling you what your IP address range is, essentially where you buy that network connectivity. They're going to tell you what your IP address is. They're going to tell you what your subnet mask is, the whole 9 yards. Now, for you as an individual that may be in a home, a small office, a medium-sized office, that type of thing, in that type of place, you're going to be using non-internet routable addresses, essentially private IP addresses that internet networking equipment know not to route. Because one of the problems you can run into, right, when you're dealing with the cloud, if you do something stupid and you set up some stupid IP address range in your network, and then that gets advertised to all of the other networking devices on the cloud, you can run into a real problem where all of a sudden traffic will start getting routed to your computers or devices, even though that's definitely not what you want, right? You want to be able to have one printer on your network be able to print to the print server on your network. You don't want all the traffic for Travelocity to be sent to your print server, that type of thing. And so basically what they've created is what are called private IP addresses. These are IP addresses where any internet connected networking equipment will simply not allow the traffic to continue. The IP address will not be broadcast. It will not be made available to the wider internet. And so this gives you some room to play with, so you can come up with your own, IP address schemes, and you don't have to worry about screwing up the rest of the internet. This, again, as with a lot of stuff, this gets a little bit complicated, You have to understand things I haven't taught you before this fully makes sense. But like one of the problems you can get to, there's something called BGP, Border Gateway Protocol. This is something called a routing protocol, and this is the routing protocol that data centers, telcos, those types of folks will use in order to route traffic through the internet. One of the mistakes that's happened in the past couple of years is for some reason, nobody understands why, there will be periods of time when all like US internet traffic or almost all European internet traffic gets routed to China. Yeah, it's surprising how that works. All of a sudden, there will be a misconfiguration with BGP on some of the routers in China. They will advertise routes that they're not supposed to advertise, and all of a sudden, a whole bunch of traffic, from Maryland to the United States or from Estonia in Europe, all of a sudden starts getting routed through China. And the reason for that is when you're actually connected to the real internet is simply a whole bunch of networking devices connected. They're much more powerful, they are much more expensive, but they work on a lot of the same principles as the networking equipment that's in your house or whatever work on. So if somebody makes a misconfiguration, all of a sudden, oops, everybody's traffic is somehow going to China for some reason. I'm not getting in the middle of this politically. I'm just saying it happens a shocking amount of the time. Right? And so here's the thing. So even if high-level network administrators screw up things like border gateway protocol and send all the traffic to China, just imagine if every, new Net Plus, person who got certified in Net Plus, what if their configurations on their local network would screw with the internet? That would definitely be a bad thing. And so that's why they came up with these private IP address ranges, and so this allows you to create IP address ranges within your own local area network, within your own enterprise, but the rest of the internet knows that if somehow it shouldn't escape, these IP addresses shouldn't escape out onto the internet, but if somehow they do, all the networking equipment on the larger internet will simply ignore those IP addresses. And so that's where, if you look at the top here, we have 10.0.0.0/A. So that's a class A subnet. And so that allows you to have addresses 10.0.0.0 through 10.255.255.255. That basically gives you something like 16 million possible IP addresses. And so you could create a very large network doing that. They have 172.16.0.0. That's a /12 subnet. So that will give you a lot of different IP addresses that you can use. Or what you'll see me use most of the time here is the 192.168, and I'll do .1, but .0.0.16. So basically, any IP addresses within this particular range, they will simply get ignored when it goes out to the wider internet. Now you'll notice, again, whenever I've been using the 192.168 subnets, I've been using a /24, not a /16, because that's how, when I divide up networks within my infrastructure, I prefer to use that third octet as the network number instead of trying to go and screw around with the fourth octet. What that means, right, is so they give me the ability to use. So they do 192.168.0.0/16. So they allow me to use the last two octets for computer IDs, and the first two octets, that's just sectioned off for the network ID. That is basically hard coded. So what I can do is, instead of using a /16, I can use a /24. When I do a /24, it goes 192.168.1.x. This now gives me the ability to create my networks out of that third octet and then use the fourth octet for the computer identifier. Again, for that fourth octet, if you only have one octet, you can have a maximum of 254 IP addresses. 254 IP addresses is more than anything that I ever need to deal with. And so when I am using multiple networks within my system, basically I need different networks for the routing, that means I can use that third octet to create my different networks. How I have used this in the past is something called DMZs, something called demilitarized zone. This isn't as important as it used to be, but it can still be very valuable, right? So let's say you have the internet here, and this comes in, and this connects to your ISP modem, right? Your ISP modem. And then what happens if you only have one internet connection, but you need to create multiple different networks to use this single network connection? So what might happen here is, so I have this router here, and this connects, to a network with different computers and devices. And then I want to put another router And then under that will be a switch that will connect to different computers and devices. And under that, I might, have another network that will connect. Why I might use this, especially if an internet connection is kind of expensive in my area, is what if I want a guest wireless network? So I want the guests at my facility to be able to use a wireless network, but I do not want them to be able to see my servers. I do not want them to be able to see the normal user computers. So what can happen here is I can create a 192.168.1.x network. So this is 255.255.255.0, right? So this is the network ID for this particular network, the first network that I'm creating. I then connect another router to this, and what I'll do here is I'll make this the 192.168.2.x network. So again, it's a 255.255.255.0, and so this is the network ID. So 192.168.1.x is this network, 192.168.2.x is this network. And then let's say I put servers there. So let's say I have like my web server. I have some other kind of servers there. I would put there. So maybe they're a little bit more vulnerable. Theoretically, they could be hacked. So I want them to be able to connect to the internet, but if they get hacked for some reason, I want to keep them separated from my internal network. So my internal network has my Active Directory going on. That's a security protocol type thing. It has my file servers, it has all my users, it has my printers, the whole 9 yards. So for this network, then I might create 192.168.3.x, again with a 255.255.255. So now this is the 192.168.3 network, and that's this particular network. Again, routers route between networks. So therefore, if 192.168.1.3, if the computers on this network need to get to the internet, this router will route up to this router, will route up to here, out to the internet. They'll be able to get their internet traffic, all that kind of stuff, and it will get routed down below. And so that's how you can use these different subnet masks and such in order to create, again, a different architecture for the infrastructure that you're designing for. Oh, hallelujah, hallelujah. Oh my golly, oh my golly. Is it over? Is this class over? Please tell me it's over. Please tell me it's over. You know the only thing worse than taking a class on subnet masking? Yeah, trying to teach subnet masking. I don't know. It just kind of cooks your brain in a way, because there's all this different crap that you have to get in your head, and half the stuff that I have to teach you is most likely going to be worthless in your career, and half the stuff is going to be incredibly valuable. But which half is worthless and which half is valuable? It's very difficult to know, which is which. And then on top of that, you got to talk about things like architectures. It's like, hey, yeah, the reason this is important is because of all this stuff that you haven't been taught yet. But to understand that, you kind of sort of got to understand this. And it just, I don't know, it just melts your brain. It just melts your brain. What I will tell you is if you do not have to take a test, let me be clear, if you do not have to take a test, use cheat sheets. Cheat sheets are fine. Honestly, what I'm going to tell you, in the real world, what you're going to find is there is going to be a way that you decide to do subnet masking, and then that's just the way that you're going to use, and it's going to work perfectly fine, and you're just going to keep using that forever. Again, like I say, whenever I build a network, it's 192.168.1.x. If I have to have multiple networks within the same infrastructure, it's .2.x, .3.x, .4.x, .5.x, .6.x. That's how I build this stuff. I just find it to be very easy. That's the private address range that I've been given. I generally don't deal with networks that have over the 254 requirement for 254 IP addresses, and so that's the way I go about things. When you go out, if you're a consultant or you're building your own network, maybe you're gonna like the 10.x.x.x network, right? And I need 16 million IP addresses, Eli. If I don't have the ability to have 16 million IP addresses within my network on a single LAN, right? Anyways, that's what you might do. I have consultant friends of mine. Whenever they build out networks, it's always the 10 dot whatever network. That's how it is. Most likely, you're going to go into your infrastructure and you're going to be told what it is. This is what it is. And again, remember, it's the technology world. It's either right or it's wrong. So if they tell you to do it some way, just do it that way, because you're not going to be reinventing the wheel. And so again, that's one of the difficult things with this kind of thing too. Is one of these it's both incredibly practical and incredibly esoteric at the same time. Like when you need to know this, you freaking need to know it. You just generally don't need to know it, right? So anyways, the big important thing here is, again, to remember, essentially, when we talk about an IP address contains both the network identifier and the device identifier. The subnet mask shows you where that ends, and basically you use the octets, the 4 octets, and wherever the ones end, that's where the network identifier ends and the device identifier begins. If you add up all the numbers in an octet, that gets you to 255. So just realize, if you have 255.255.255, that means the first 3 octets of the IP address are the network identifier, and the last octet of the IP address is the actual computer identifier there. If it's 255.0.0.0, that means the first octet is used as the network identifier. The rest of the octets are used as the computer identifier, and you go from there. Again, you can subdivide. So if you were given a class C subnet, a /24 subnet, and for some reason you need multiple networks out of that, that's where you can go to a /25, you can go to a /26, and then you can subdivide that way in order to create your router scheme and your architecture and go from there. The important thing to remember, the thing that really screws new people up, is sometimes they forget what the hell networking equipment does. And the important thing to understand is routers route between different networks. If you have 192.168.1.x on one side, and you have 192.168.1.x on the other side, the communication is not going to work properly, because you have, as far as the router is concerned, you have 2 networks on each side of the router. So there's nothing to actually route there. Again, one of the other things to be thinking about, this is 50-year-old technology at this point. So theoretically, you could have a single switch. On that single switch, you could have 2 IP address schemes. So you could have 192.168.1.x for some of your computers, and you could have 192.168.2.x, /24 with some of your other computers. Although they're on the same switch, and although they're within the same collision domain from an Ethernet standpoint, as far as TCP/IP is concerned, they're not going to be able to communicate with each other. And so that gets into its own world. Would you do that in the real world in the 2020s? Probably not. But again, it's an important thing to understand how all this different technology is layered on each other and how you could run into problems. Again, when I talk about that, that's not VLANs. There's something called a virtual LAN. A virtual LAN is a way to logically divide your switch, actually at that layer 2 level. This is not that. This is up there at the network level, the layer 3 level. Yeah, and then finally, like I say, the private IP addresses, the 192.168 or the 10. Whatever, those are the standard private IP addresses that you can use. That's what you're going to be using, and whether it's the enterprise or whether in your home, that's generally what you're going to be using. There is the other IP address scheme I didn't talk a lot about, was 172.16. This was actually opened up as a private address scheme in 2012. Be careful of using 172.16 though as an address scheme, because apparently not all networking equipment knows that it's supposed to be routed at this point. One of the problems you run into in the real technology world is standards can change, but if you don't upgrade the firmware for your equipment, or if you can't upgrade the firmware of the equipment, even if the technical standards changed, the equipment is still going to be doing what it did. And so with the 172.16 range, a lot of networking equipment actually will not deal with that range appropriately, simply because you may have networking equipment that you installed back in 2005 that's doing fine. If you never upgrade it, if you never fix the firmware or anything like that, you put 172 onto your network and it may not know what to do with that particular private address range. So I would tell you, stay with either the 10.0.0.0 range or the 192.168.0.0 range. That will be better for you. And if this is very confusing, keep following along. And maybe sometime in the future, maybe a month from now, come back to watch this particular class. Yeah, and again, it's just one of those things. Don't worry about it. Again, I deal with IP addresses every day. And I swear to you, like this whole subnet mask, I have my little cheat sheet up on my computer over here. Because even though I deal with it every day, it's like there's dealing with it and then there's dealing with it. Anyways, I think you get what I'm saying. So anyways, as always, I enjoy teaching this particular class. Well, no, I didn't. That's a lie. That's a lie. Proof that even Eli the computer guy lies to you every once in a while. It sucked teaching this class. I never want to teach this class again. This is the last time I'm ever going to teach subnet masking. I'm done. I don't care. It sucks. But anyways, normally I enjoy teaching these classes, and I'm going to come back. I'm going to do another class that I enjoy teaching. Not subnet masks. Anyways, see y'all later.